Okay, so let's continue. Up to this point, we've discussed motion, for example, of particles in a curved metric. We also discussed the possible forms of the metric. So let's just very briefly recap before we move on. So remember that the equation of motion for any particle under the influence of gravity in general relativity is essentially just the equation of motion of a free particle but in a curved space-time. And the equation of motion we could write in the following way. Like this, where this is the proper time measured by whatever particle we're looking at. Then we have these Christoffel symbols that all encode various first derivatives of the metric. And we saw during the exercises actually an example of a completely flat space, namely a plane surface, where in polar coordinates you get non-zero Christoffel symbols, and that leads to equations of motions that are equivalent to the ones that you normally get in classical mechanics in polar coordinates, where you have the appearance of a fictitious centrifugal force. Of course, this generalizes to arbitrarily, if you want, weird spacetimes with lots of curvature and time dependence and so on. This equation is completely general. Now, in order to actually solve the equation of motion, of course, we need the metric that we should be working in. And we saw that a metric which is 3D symmetric, meaning that it obeys the cosmological principle, so it's the same everywhere, must have the form of what is known as the Friedmann-Robertson-Walker metric. So it's possible to write it in such a way that you separate space and time coordinates. The spatial part of the metric expands or contracts with time. Therefore, we have to introduce the so-called scale factor. And then on top of that, we have the radial part, and then, if you want, an angular part which encodes possible curvature of space. So that's one possible way of writing out the Friedmann-Robertson-Walker metric, where we now have a function that depends on the sign of the curvature. So this S kappa function we could write as, for a closed universe, as r times the radial coordinate divided by r, where r is the radius of curvature of the metric. So that's the case for kappa equal to +1. Then it's equivalent to just the radial coordinate in the usual case where the three-dimensional part of the metric is just Euclidean. And finally, we have the open solution where we get a sign hyperbolic like this. And that's basically all there is to it. That's the only metric you can have in a space that obeys the cosmological principle, meaning it's homogeneous and isotropic, and which is, as we call it, simply connected. So it has no, for example, holes in it. And that means that we have now fully specified whatever metric we're working in, but we are missing, of course, a lot of stuff, because we don't know, for example, how would we calculate, how on earth would we calculate A of t, and how would we know what sign the curvature has and what the curvature radius is, for example. We have no clue as to how to do that. And that's, of course, because we have only just started on this road. So we have basically done what you often in physics call kinematics, so motion of particles under specified forces. That's what's equivalent to the geodesic equation. We have specified the metric that we must be working in based simply on symmetry properties, nothing else. But we have not yet introduced what you could call dynamics. So we don't know what the force law is, for example, that governs everything that goes on here, right? So in Newtonian terms, that would be the equivalent of Newton's law of gravitation. We don't know that. And in GR language, it means we don't know the field equation. So we don't know the equivalent of Maxwell's equation for the gravitational field, in this case meaning the metric. But whatever it is, it must be a differential equation of some sort. And in order for us to be able to extract Newtonian mechanics from it, we already know it must be at least a second order differential equation. It could have higher order terms for all we know. That must just go to zero in the Newtonian limit, but at least it must be second order. And as it turns out, of course, there are many ways in which one could write that differential equation. So whatever it is, it's some kind of differential operator. And the fundamental object that must be working on is the metric, right? So that's how it must be. And then there must be some source term over here on the right-hand side, whatever generates the gravitational field. So in Newtonian physics, that would be the presence of mass, for example. So schematically, that must be what it looks like, whatever equation we're looking for. And it turns out the simplest equation that you can write that has second-order derivatives and is covariant, meaning transforming under Lorentz transformation in the appropriate way to conserve special relativity, is what is known as the Einstein equation. And the way schematically it's written, it's a tensor equation. So these are rank 2 tensors, as you can see. It's some kind of differential operator there that I'll specify in a minute. And then there's a source term here. So this G mu nu is just formally called the Einstein tensor. And of course, if you take the course on general relativity, you'll go through this in much more detail, and you'll actually see that indeed it is the simplest covariant form that contains second derivatives that you could have on the left-hand side. But let's instead I'll just write it out, and so you can see what it looks like. And I will only do it this one time because it's quite cumbersome. So it contains a new tensor, which is called the Riemann tensor, and the trace of the Riemann tensor. So this actually is just the trace over that tensor, right? So that's a scalar quantity. And this Riemann tensor can be constructed from the Christoffel symbols by appropriately, and that's not very surprising. Now let me just write it out again this once. Okay. Yeah, there are a lot of terms. Okay, that's it. So as you can see, we know the Christoffel symbol contains only first derivatives of the metric tensor. And that means this is a second derivative, this is a second derivative, this is a square of two first derivatives, so it's also second order and derivatives. And the same for this final part here. So altogether it contains a lot of second derivatives of the metric tensor, exactly as we would want it, right? So there are no first order term, and actually there are no higher order terms. So it's the simplest possible choice you can make that is still covariant. So it has the right transformation properties. So far, so good. So that's the differential operator that we have on the left-hand side. Then on the right-hand side, we have a source term of some sort. But before we go to that, let me just briefly, and we don't have to talk much about it at this stage, but let me just briefly touch upon the question as to whether this is actually the most general form that you could imagine. And the answer is no. Actually, there are many other ways in which you can do this. So for example, you could have higher derivatives. So you could have third order derivatives, fourth, fifth, sixth, so on. Why not? That could still be made to transform in the appropriate way but we don't need it. So Einstein's original postulate was that they are not there. But of course, this is something that in principle should be checked. And indeed, that has been done in many cases. One problem is that higher derivative operators are typically associated only with extremely strong gravitational fields, so black holes basically, and therefore difficult to test. But we now actually have a test of it because we now have gravitational waves that are emitted from coalescing black holes. So that's the extreme strong field limit of gravity, and that's where you can actually test higher derivative theories. And that has basically killed off not all possible theories, but most of them, and left normal GR as the winning contender, if you want. There's another possibility, which is cosmologically perhaps slightly more interesting, and that is the fact that this is a scalar function, and therefore any other scalar function that you put here, some other function of the Riemann scalar here, would transform in the same way under Lorentz transformations. It's just a number, right? And that would mean you could in principle construct a model, this is a whole class of models called f of r gravity, which has a different property than general relativity in the extreme weak field limit, which is interesting for cosmology because after all that's where we have very, very weak gravitational fields, but where we have very large distances over which they can act. And that would be potentially be interesting here. And I can say already now that this is one possible explanation for the presence that we see of dark energy in the universe. One possible solution to that conundrum is that in fact it might be a modification of general relativity rather than the presence of a real physical energy in the universe. We don't know that yet, but it's a possibility. But for now, let's just work with normal general relativity, and then here and there I will try and make contact with this possibility that GR has to be modified in order to explain dark energy. Okay, but so far so good. So the next part, of course, is the right-hand side. That's the source term for gravity. And that must, of course, include energy in some form. It cannot just be non-relativistic matter, right? Because we know already in special relativity there's an equivalence between energy and mass, and the same of course must hold true in general relativity, and therefore whatever, if we just write it out, whatever is on the right hand side cannot just contain rest mass, it must contain energy in some more general form. And actually one can show that this tensor over here, which is called the stress tensor or the stress energy tensor, contains various forms of momentum transport, either along the time direction or along the space direction. Transport of momentum along the time direction, that's just energy. So if I write it out, and now I write it explicitly with one index up and one below, remember that you can of course get the one with two indices below by acting with the metric tensor on this other thing here, right? So you could get, for example, this thing by acting with the metric tensor on the one with one raised and one lowered index. So these two are not equivalent unless you have the identity matrix here, which of course we know we don't. So it's just to say that there actually is a meaning to writing upper and lower indices. Just be aware that they are different things. Okay, but in this notation with one up and one down, one can actually write out the metric, the stress energy tensor. The term up here in the very left corner, that's the time component, actually turns out to be the locally measured energy density for an observer at rest in the system that we're looking at. And what we have down here on the diagonal is, for example, pressure measured in the x direction. So that corresponds to momentum, if you want physically, to momentum propagating in the x direction, measured along the x direction. And that indeed, of course, is pressure, right? So momentum transport, that's force, and then force across an area, that's pressure. And that's exactly what we have here. So this is the effective pressure that we have in the x, y, and z direction in the system. So of course in a homogeneous and isotropic system, these must be identical, right? You must have the same pressure in all directions. But this is not necessarily the case. You could imagine, for example, that you have a gas flowing in a tube, right? So that has a different pressure along the direction of motion and compared to the transverse direction. So that's just one example. So generally speaking, it's certainly not the case that they are identical. Now up here, we will have, again, energy, that's the time component, but transported along a spatial direction. So this is what corresponds to energy flux. So energy transported in some direction, either x, y, or z. And the same is down here. Now, for example, if I take this term, that's an x, y component. So that would correspond to momentum, for example, in the x direction, but being transported along the y direction. So this is a term that generates vorticity in the system. So it generates rotating motion in whatever fluid I'm looking at. So these terms are often called shear or anisotropic stress terms. And I should also here say that this so-called stress energy tensor, that's actually something that doesn't only appear in general relativity. This is a well-known quantity from special relativistic hydrodynamics. So something that is completely well-known from, if you want, normal fluid mechanics. And even if you go to the non-relativistic limit of this system, then from the stress energy tensor and its conservation, and we'll see that a little bit later, you can actually derive the normal fluid mechanics equations, namely the continuity equation and the Euler equation, the Navier-Stokes equation, and so on. So this is actually something that is much more general than stuff that has to do with gravity. This is something that you use also, for example, if you're looking at wind flow across an airfoil of some sort, either a wind turbine or a plane, for example. It's exactly the same thing. It's the same equations that you get out, but of course without gravity involved, right? So that's the only difference. Okay, so far so good. Now the question is, what would this so-called Einstein equation actually look like in the system that we're interested in? And we can already sort of guess that it must be simpler than the most general case, right? So we can already guess, for example, that energy flux must be zero. Because if you have a system that obeys the cosmological principle, it means it's homogeneous and isotropic. So it's everywhere the same. So the only flow you can have anywhere is along the time direction, so to speak. And that means that such terms as here cannot exist, right? Because if you have energy transported from one location to another, then that must be compensated by exactly the opposite flow in the other direction, because otherwise you would violate homogeneity and isotropy. The same is true here. These terms are also zero. The only things that survive are the diagonal terms. The local pressure, for example, that's certainly non-zero, even if you have homogeneity and isotropy. But what we do know is that they must be identical. So altogether, this big nasty tensor, which in principle would have 10 independent components, right? It's a symmetric 4x4 matrix, so it has 10 components. You end up with only two. You end up with local energy density and pressure. And normally in GR we refer to energy density as just rho. So I'll use that terminology from now on. So we have rho and p as our fundamental parameters. And that of course also means that when you look at the full Einstein tensor over there on the left-hand side and you write it out, you must end up with only two independent differential equations. That's all you can have. I mean, there's no more information embedded in this equation here. And of course you can now just sit down and write out all the terms. And you can do that actually based on the information that you have available, right? Because we know what the Riemann tensor looks like. We know how to do the trace of the Riemann tensor. So we know all there is to know. And we can do that. And what we end up with is, for example, and we'll use that in just a minute, the 0, component of the Einstein equation. That ends up being what is known as the Friedmann equation. And the Friedmann equation you can write as a simple differential equation for the scale factor. So this is normal coordinate time derivative of the scale factor. Then on the right hand side we indeed have a source term, which of course now it's the 0, component. So the stress energy tensor only contains the local energy density. So that's it. Then there's a factor of 3 that I've divided through with. It actually appears over here, and then I divide through with it. And there's one more term, as it turns out, on the left-hand side that is traditionally moved to the right-hand side. And that's a curvature term. So actually what happens is that the sign of the curvature and the curvature radius appear here. So for a flat model, this term of course is 0. So this is the so-called Friedmann equation. That's, if you want, the fundamental differential equation in normal standard Big Bang cosmology. It's the one that tells you that if you have some kind of energy density, then how does the universe expand with time? Of course, we cannot yet solve that equation because we don't know what kappa is, for example. We don't know what r is, and we don't know how the scale factor evolves, how the energy density evolves with scale factor. So that remains to be seen